Hello, this is a review for CS202 material. In this video, I'm going to be covering all of the topics that we covered in CS202. You can see in the YouTube description that this will be timestamped, so please feel free to click around and go to whichever topics you feel like you need to review more. This video is not intended to replace normal instruction, so if you're watching this in place of actual lectures that you haven't watched before or were there to experience in person, then I highly encourage you to look at those first, since we are going to be taking more of a quick look at topics that we covered in the course rather than go into any details. So this is intended more as a supplement than as an actual lecture. That being said, let's go ahead and start at the beginning where we started in this class, which was with object-oriented programming and objects. In CS135, you left off with the idea of a struct, which you could write by doing the keyword struct, followed by the name of the struct. So you could do something like struct person, and then within that struct, you can put both variables and functions. So we could do something like this, where we say a person is something which has a name, which is a string, and a age, which is an integer. And the person might also have functions that belong to them, actions that they can take. So we can say, like, say name, which takes no parameters and prints the name. Right, something like that. And so the idea with a struct was that it's a container for your attributes and your actions. So we could say the variables here are the attributes, and any functions, of which we only have one, is an action. The struct itself is simply a blueprint. It doesn't actually make any data get allocated. This doesn't create any object or any actual usable variable. However, it defines how this variable will work if you were to make more later. And as such, we sometimes call structs and classes user-defined types, because it's a type that you, the user of the programming language, the programmer, are creating. So whereas an integer and a float and a boolean are all built in, the computer understands what those mean, classes and structs are data types which you define and you describe how they work. You describe, these are the variables which belong to this data type that I've created. These are the functions which belong to this data type, or at least associated with it. And if I want to create an object of that type, then I can do so. Right? So just like you could write int x to create a variable called x, where you put the type followed by the name, you could do the same thing with your custom data types, your structs and classes. And what this means is that this person that we've defined has their own name, their own age, and the ability to say their name, right? And every single time you create a person, so we could go down here and create a second person, their name and their age are completely unique. So I can do something like, say, p.name is equal to John, and q.name is equal to Jane. And these are distinct. They belong to the object that the dot is being applied to, right? So if I say p.name equals John, I'm creating an object called p, and its name becomes John. And then I'm creating an object called q in my code, and that object is one whose name is Jane. So whereas our class and our struct declarations are simply blueprints, they describe how this type should be constructed if it is, when we actually go to use it in our code, when we say, please make a variable of this type, make a person called P, and then here's their name, and then the same thing with Q, that actually creates the object. So this also applies to our primitive types, right? The integer is a predefined thing. We have an understanding of what it means for something to be an integer in math, right? It's like a discrete value. It's counting numbers, right? Positive or negative. Same thing with a person. We're just saying this is how it works. And then when we actually want to make a person and be able to use them, that's when we create a variable this way, right? And so this process was known as instantiation. And these guys here, the P and the Q, are either referred to as instances or objects. It's interchangeable. But the idea is that they are specific things that exist. They have their own self-contained name, their own self-contained age. They have their own attributes which belong to just them, as opposed to the structure class, which is just a description of how they're made. And so this is where object-oriented programming comes, is that we create these objects in our code and we have them interact with each other. We ask them to do specific actions, right? So they have their own separate, variables and things that they can do. While we're defining terms, the process of, I guess not process, but the idea of putting all of these things into a single package, grouping them together, has two different terms. It's either referred to as aggregation, where aggregate in English, right, just means to put things together, and encapsulation, which is the idea that everything is together in a bubble. Either of these terms are fine. They have slightly different meanings, but they're relatively the same. So kind of the point of our structs and our classes is to aggregate or encapsulate data and put it all in the same common place, sort it under a common moniker. That way, we can group it together, right? It's more beneficial if I know I'm going to need a lot of persons in my code to have a person object rather than make a huge array of strings for the names and a huge array of ages. And that doesn't really scale well as we have more and more attributes that belong to this object, right? It's better to organize them so that we can understand, and then let the compiler take care of the technical aspects where it actually puts those into like a common data structure. Right, so this was our idea of an object. After that, we discussed the different types of modifiers that we can apply to these variables. So a struct and a class are functionally identical in C++ specifically. Not in other languages, but in C++, they're basically the same thing. They aggregate data together. And these are either user-defined data types that we said before, but the specific kind of user-defined data type that they are is an abstract data type. And the difference we had between a class and a struct in C++ specifically is that a struct has public members by default, whereas a class has private members by default. And that's the only difference between these two things in C++, is that all of the members, that is the attributes and actions, the variables and functions that belong to a struct, are going to be public by default, although you can make them private. And then the same thing goes for class. They're private by default, but you can certainly make them public or protected. There's no limitations on what modifiers you can use on these members. However, this is just if you don't put any and you don't tell it explicitly, this is the modifier that I want, this is what it assumes you want. A lot of the time, we want private members. So from CS135, where we use structs because it was easy, everything was public, nothing was restricted. We use classes because as we organize code, we want things to be private. And so private, as a modifier, you can use it before a set of attributes and actions to say that all of those things are private. So you do private and then a colon. And what private means is it's only accessible within the class, save for when we use the friend modifier, which violates access modifiers, right? The friend modifier makes it so that private protected doesn't mean anything. So these are only accessible in the class they were defined in. I guess maybe defined is not the correct word, but declared in. This may be appropriate. And this was shorthanded with a minus. Then we had the next most restrictive, which was protected, which meant that it was accessible in the class it was defined in, or I guess declared in, plus any derived classes. And then finally, the last access modifier that we had was public, which is represented with a plus for shorthand. And note that these minus, sharp, and plus don't work in C++. These are just when you're writing things out to describe a problem when you want to give it to somebody else. Right, just describing the classes that you intend to write, which meant that it was accessible everywhere. So the reason why we started with structs in CS135 is that it would require the explanation of what private protected mean, and just to keep things easy, we stayed with public. Because there are no limitations on what you can do with a public variable. And the purpose of using these was to hide data. Which, if you look in documentation, online, or in resources, you'll see this referred to as either data hiding or accessibility. And what we said was that this provides no actual security benefits. All of the data is treated exactly the same way. It isn't encrypted. It's not stored in a specific way. All this does is provide ways for programmers to limit the scope in which members are used. So if you want no restrictions, you want a variable or a function to be accessible everywhere, and there's no problem with it being used anywhere, then you should make it public. However, as we learn how to encapsulate things, how to aggregate data into classes and structs, we realize that, well, some of these functions and some of these variables don't really need to be used by any other programmers other than the one who is writing that specific class. Right? You might write something where this variable is shared across functions within a class. However, if it's modified, the code will break. And so you don't want anybody accidentally breaking it. You want to give them peace of mind and not require them to look through all of your code and understand how it works and just think they have an idea of how it works and touch a variable that's not supposed to be touched. And so because of that, you might mark something, either a function or a variable, as private so that any outside programmer, even yourself, does not modify data which should not be modified. So you can hide your data or restrict the accessibility of data and functions so that it is only accessible specifically in that class. And this will mean that if anybody does try to use it, the compiler will tell them, hey, you're not allowed to use this. And on top of that, if you're using an IDE like Visual Studio, where it gives you recommendations on what code to write, it will hide that data from the suggestions because it knows it's not accessible there. So you can also make your programming easier by simply hiding the data because you know it's not relevant outside of the class. Right? So obviously we're not going to explore this in detail. We're just taking this at a high level look. However, as you program more and more, you will find that, yes, I do want to make a lot of these things private because it makes it less susceptible to making bugs. You are less susceptible to use the wrong variables if you intend for them to be accessible only within the class. So again, just to reiterate, really want to stress this. No security benefits. This does not modify the way that variables are stored in memory. All this does is give the compiler some information about how it expects your members to be used. And so those were our accessibility modifiers. We had a few other modifiers, but the main one that we were concerned with while we were talking about object-oriented programming was static variables. Earlier, we had the name and the age of a person. So we had a person named John. We'll just arbitrarily set their age to be 30, and then Jane, whose age will be, let's just say 26. And so the idea here was that these variables belong to these specific objects. The name of P is John, and the name of Q is Jane, and they're non-overlapping. They're specific to that one object in our universe, right? But we might also have variables which are not tied to any specific object in our domain. And so in this case, maybe we have a count of all the persons that there are. However, that person is not a descriptor of just John or a descriptor of just Jane. It's a descriptor of the whole population, and it's a descriptor that doesn't really need to be associated with any one object. And so the way we refer to these variables is that these ones, which belong to an object, are referred to as non-static, or alternatively instance members, because they're within an instance or an object. As we said, that's the term for these specific bubbles here, right? And these variables, which are not tied to a specific object, are static. And so don't be confused by the physics term static or just the general English term static. A common mistake I see on this is that some people get the word static here confused with const. Remember that const means a variable which cannot be changed over the runtime of a program, but a static variable does not have that requirement. Consts are static, but static variables are not necessarily consts. Just like, a rectangle is, or a square is not necessarily, I butchered that, I'm sorry. A square is a rectangle, but a rectangle is not necessarily a square. We have the same case here, right? A const is static, but a static does not have to be const. But what a static means, right, is not tied to an instance. In the context of variables, this is usually appropriate when we either want to describe all objects in our domain or when it's something that everybody needs to look at. A common application of static variables might be you're writing a video game. The player is an important variable within the program. However, it's its own class, right? You might create a player class. So you might create a static reference to the player. That is like, here's a pointer to the player so that everybody knows exactly who the player is. They have their name, their reference via the pointer, and they can always access it. So it's either a descriptor of the population like this count, or something which is just generally useful and needs to be shared across everybody, but isn't tied to one specific thing. Right, and so non-static just means the opposite of this. It means we would, X out the not, and it would be tied to an instance, which makes sense here because John and Jane and 30 and 26 are attributes which belong to that one specific object. And so we can declare variables by simply putting the static keyword in front of it, and then it will mark it as static and tie it to an instance. So we could do something like this, where we say class person. And within that, we have our non-static variables for the name and the age, which are private. And then we can have something like the count, which would be static. And we put the word static in front of it, and then int count. While we're still on the topic of classes, remember that we talked about constructors, which are functions that have the same name as the class. So if the name of the class here is person, the constructor is like this. And these are special functions which are called specifically when an object is created. And then we also have destructors, which are maybe not relevant here yet, but those will allow us to execute code when something is destroyed. So a constructor is when something is constructed or created, and the other one is when it's destroyed. So we can create a public constructor, keep these variables private, and then we can have something like, void, say name again, and then write the code for that as we did before. And then we can have something else like, for example, say static person who is older. Between person 1 and person 2. And then write code that does that, right? Just compares their name and returns the person. Not the point. So variables, as well as functions, can be static and non-static. A static function is one which is intended to be executed by the object. Remember, our definition of static we had earlier is that it is not tied to an instance. So non-static means it is tied to an instance. When we're talking about functions, non-static means that the instance is the one who is doing the code. They're the one who is executing things. They're the one taking the action from a high-level view. Whereas static means that nobody in particular is taking an action. So this might be things that involve multiple objects within the class, right? In this case, we're telling who is older. Then, John isn't the one who's doing the comparison, and Jane isn't the one who's doing the comparison. They're kind of doing it together, right? Things like sorting might also be appropriately static, because if you're sorting an array of persons by, let's just say, their age or alphabetically or something like that, then no one person is like organizing everybody together, right? It's just a process that is being done on the people, and it's being done on all of them, right? So you might make something like that static. You might use something that uses multiple objects as static. You might also do something which is just a helpful function related to all objects of that type, right? So you might have mathematical formulas. You might have like a geometry class, right, where you just include the Pythagorean theorem because it's useful for a lot of different things, or like a distance formula, which is related to the Pythagorean theorem, and it's just, it's a function which exists there, and I could have written it as global, but I'm writing it as static so that I can tie it to the class. I can, organize it in this class here between these curly braces, but just anybody can use it. It's not tied to one object. And then our usage for this was for static variables. So something like our count here. These are a little bit strange in C++. We talked about, let's use the const express keyword. You have to do something like this, where you say int count equals 0. Whereas if I wanted to access the age of a specific person, I have to have the person whose age I want to talk about, right? I can't just say person age, because whose age am I talking about? Am I talking about John's? Am I talking about Jane's? Am I talking about a mysterious third person, right? You can't know that. So static variables, you simply say the class name, colon, colon, and then the variable, whereas when we have something that is non-static, it needs to be tied to an instance, so it's the age of a specific person. Right? So if you know that it's belonging to one specific object and it's non-static, then you need to use a dot or an arrow operator. If it's static, you can technically use a dot operator, but you shouldn't. Instead, put the class name colon colon. And I am cheating a little bit. This doesn't really make sense in this context, but just for the later example, we'll say that. Right, and then the same sort of thing applies to our static and non-static functions. If I say p dot say name, then John will say just his name. This won't print Jane, it will just print John, because John is the one who's saying his name. And this is where this maybe makes the most sense. John is the one who is saying his name, hence why he's the one who comes before the dot. The thing before the dot when you're calling a non-static function is the one who is doing the action. They're the one who is responsible for executing that function, and from a high level view is just the one who's doing the action. Right, so here we can't just say name, because whose name are we going to say? We need to put p dot say name to say specifically John. John's name is the one we want to say. Same sort of thing with static functions as are static variables. Because it's not tied to an object, you don't need to put an object beforehand, but you still need to specify where it came from. So we do something like person, which is the name of the class, and then, sort, what if we said something like who is older? Between P and Q. And again, this has the class name before it. Okay, so these red ones are static, and these blue ones are non-static. So that was our other major modifier that we applied other than public, private, and protected, which were accessibility modifiers. This static allows us to either tie it to an instance or just let it be free-flowing. And then we had rules for these, which we won't go into too much detail on for now. We'll just keep it high level. We have the members. Maybe want to make this a little bit higher. And then we have the scope, which could be static or non-static. Right, so we could have static members, static functions and variables. Static variables can be used in a static scope. If you have a function which is not tied to an object, you can use other variables that are also not tied to an object. If you have something that is non-static, you can also use static members. So even though John and Jane have their own name and their own age, they should be able to access the count because it's just information that's out there. There's no reason why they shouldn't be able to do that. Same thing with a non-static scope and a non-static member. So if John and Jane are executing a function, which they are specifically the ones who are doing, John is going to work, John is saying his name, then he should be able to access his name as well, right? He should be able to access non-static members. However, the one case where things are not accessible is when we try to use non-static members in a static scope. So say we're trying to sort through our list of people by their alphabetical order. We have like an array of persons, for example, and we're trying to figure out what their names are in alphabetical order. Then we need to know whose name we're talking about. If we just say name, then whose name? John's, Jane's, the 40th person in the array, the 30th person in the array, not really clear, right? So that doesn't really make sense. You need more context, and so you cannot use non-static members in a static scope without having an object reference. You need an object to figure out whose member you're getting. You need to know it's P's name that I want, it's Q's name that I want. You can't just say name and expect it to know what that means. So we did examples of this in class. That's why I'm not drawing out more things, but just as a reminder, that's how that worked. The next topic we did was inheritance. And inheritance is when we have classes which are related by an is-a relationship. So for example, we might have a class hierarchy diagram like this, where an animal class is created, and then we create two classes which inherit from it called cat and dog. And these are conceptually used to represent is-a relationships. A dog is an animal, a cat is an animal, but the other way around is not necessarily true. And what this allowed us to do from a programming point of view is borrow functions and data from a common class and have it carry over. And then we have the option to make unique variables if we want. So we could do something like this, say class animal. And then have a name for it. And then something like a public constructor. And if you'll forgive me, in the interest of not having to write too much, we'll just leave this as string n, which we'll say initializes the name. And then we can inherit from that class when we create a new class. So I could create a cat class here, have it publicly inherit from the animal class. And what this will do is any members, variables, and functions which belong to the animal class now get carried over to the cat class. So all of that data just gets carried over. And here in C++, we do the colon for inheritance, and then you specify a modifier on this. Again, we'll keep it simple since we did talk about it in detail, but remember the way this works is that it will compare this modifier to whatever the modifier on each variable was. So when it goes to import the name to the cat class, it will compare public with the one that is on this one, which is private because there's nothing specified and classes are private by default. And it will choose to import the name as a private variable. It will pick the most restrictive between the two, private being more restrictive than public. And when it goes and imports the animal constructor from the animal class to the cat class, it will import it as public because it will compare public here in the public that it actually is, and it picks the most restrictive between those. They're exactly the same, so it just picks public. So the idea here, remember we talked about this in detail in class, but we'll keep it high level, is just if you do public accessibility, when you do inheritance, all of the modifiers from the base class or any base classes will just stay the same, which is probably what you expect and what you want. So that's the way we do it in C++. It's a little annoying, but it's just the way that this language works. Right, so that allowed us to inherit all these variables. We can get this common data types and move them over. Right? So it makes things convenient. It allows you to have classes where you don't have to keep rewriting the same variables and functions over and over and over again. You can share them amongst different classes. If I need to write a cat class and a dog class and a bird class and a lizard class, I don't have to write string name 4 times. and it makes it easier for me to be able to expand later if I add further animals. So any code that belongs to the animal class can be borrowed later. Inheritance also allowed us to utilize data types to store different kinds of variables or different kinds of objects within the same variable. So using the same example, I can do something like this. And this does require a pointer in C++, but it is a little easier in other languages. And, well, let's actually make this an array. So let's say this is an array of 4 things. We can make object 1 a cat, and object, oh, I'm sorry, this is an array, right? So I need to actually put indices A0 and A1. And make that a dog. And what this allows us to do is have a common data structure. We can create an array of 4 objects. And the first object can be a cat, the second object can be a dog, the next one can be a cat, the next one can be a cat. And so this allows us to have a common variable or common data type for our variables, and then store either interchanging types of objects or store things of different types in the same data structure if it's an array or a vector, or now that we understand linked list or any other data structure, you might learn heaps, dictionaries, whatever. Right, so this allows us to say arbitrarily, I want 4 animals, but I don't care what kind of animal they are. It could be cats, it could be dogs, it could be birds. Throw them all into the same animal array, and it's fine that they all get stored next to each other. This wasn't the case before we had inheritance. If I had an array of integers, I can't put a float into that integer array without compromising. I can't put 4.5 into the integer array. It gets rounded to either 4 or 5, right? It gets truncated or rounded. So you didn't have that flexibility before, but once we have inheritance, we've introduced the ability to have polymorphism. You can use the same variable to represent different kinds of things, which is insanely powerful and led into us doing a lot of other things later in the course. So while it was nice in inheritance that we can borrow members, it was even nicer and very, very important that it allowed us to store different types of things within the same data type, whether it be a variable, a single variable, or an array. And that was insanely powerful. Right, so that was our idea of inheritance. I'll come back to pointers later. I'm actually going to wait maybe a little bit on that just since we're on this topic. The next thing we talked about, I believe, was virtuals. And this is related to that. So really quick, let's just say we have those animals again, and we want them to behave differently. How inheritance allows us to work with this is we could have something like an animal A, and then some code which depends on an external factor. In this case, the external factor is cin. Cin is the keyboard, or at least standard in, whatever it is. It could be file too, I guess. And so by looking at this code, where we read in from cin, we can't really know what it does until somebody actually sits down and defines what cin is, whether it's the keyboard or a file, and then actually types something or gets something out of that file. So there's no way to know exactly what this code does just by looking at it. And this was one of the other advantages to using inheritance, is that you can have a common variable. We have this A variable here, and it has the flexibility to be either a cat or a dog. Because of inheritance, you can store any derived class in a base class variable. Right, so we have that flexibility. All we're saying is that A has to be an animal. We don't care what kind of animal it is. As long as it is an animal, it has and is a relationship. And what this allowed us to do is, once we introduced virtuals, is we can have specific code which corresponds to that class and then have that execute. And our runtime environment will figure out what to do based on the object itself. So here, if I say A make noise, this will meow if it's a cat, if x is less than 0, and if x is greater than or equal to 0, then it will bark. We haven't written the code yet, but the idea with a virtual is that you can have a variable do different things depending on the context of what it actually is. So when we actually wrote the code here, what this allowed us to do was write an animal class with the members we described earlier. So we'll kind of leave that as is. And we can mark it as virtual. We can say something like void make noise. And maybe an animal doesn't make a specific noise, so let's just put a question mark for now. But then when we have further classes, if I write class, sorry, not animal, cat, which inherits from animal, with a virtual function, which make noise is, we can go into a derived class and we can rewrite how that function works. So instead of making some unknown noise for an animal now, we can say that the way a cat makes a noise is it meows. And then I could do this again, make a dog class. And write the rest of it, right? So that the void make noise does a bark. And so what this allows us to do is we can have this common data type where we can store things. I can store both a cat and a dog in an animal data type because they are both animals, but then I can allow them to do behavior specific to their class. So I can guarantee that every animal can make noise because the animal class contains a make noise function, but because it's virtual, the way that that make noise function behaves will differ between different objects of a class. This is one specific application. We also talked about this with the shape example in class where we said, you can have a shape class with an area, and all shapes have an area, but we have no idea how to take it. And a rectangle is length times width, and a circle is pi r squared, and a triangle is 1/2 base times height. So you cannot know these until you have the variables that belong to that class and then the specific formula. So we know we want it to have an area, but we don't know how it behaves, so we'll wait and then define it in a derived class. And this was really the power of doing a virtual, is that it allows you to have behavior which is modified and changes depending on how the derived class wants it to be. On top of virtuals, we also talked about abstract functions and abstract classes. I would argue in this case that an animal should both be an abstract class and have abstract functions. In C++, those two things are tied. However, in other languages, you can make an abstract class without it necessarily having abstract functions. But a thing that has an abstract function has to be an abstract class. So just to define these words really quick, so we'll mark this abstract function here. In C++, there is no abstract keyword. You put equals 0 to represent that something is abstract, which is not obvious. However, just to define what these words mean, virtual meant that a function could be redefined in a derived class. And remember that these only apply to functions, not variables. And the word for this was overridden. And what abstract meant was it is a specific kind of virtual thing, sometimes called pure virtual in C++, where it has no definition. At least when applied to a function. When it talks about a class, it just means it cannot be instantiated. So this is the function definition or abstract. Whereas for a class, it means cannot be instantiated, which means we can't use it with a constructor, we can't use the new keyword on it, we can't declare a variable of that type. So either a class or a function can be abstract. In this specific case, the make noise function makes sense to be abstract. If we're talking about animals making noise, we know that a cat meows and a dog barks and a duck quacks. However, if we just said, what noise does an animal make, you would think, well, I need more information. What are you talking about, right? So it's not specific enough, and we have no idea what that behavior would even be. In the context of our shape class, right, we said the area is something that you can do on all shapes, but I need a formula or like an expression to calculate it. I know that the area of a rectangle is length times width, and I know that the area of a circle is pi r squared. But if you say find the area of a shape, you need to give me more context. So it's not really clear how that function works, but we know we want that function to exist, and that's where an abstract function makes sense. An abstract class in C++ is one who has any abstract functions. In other languages, you can put the word abstract in front of a class and just denote it this way, even if you don't have abstract functions. But the idea here is that this class is not specific enough to exist. We don't really want it to just exist by itself. It needs to be more specific. So similar to our last example, we know that a cat meows, but we don't know what noise that an animal makes if it's not a cat or a dog or a duck or some specific animal. And so this class is not specific enough to exist on its own. If you're going to make an animal in your code, it has to be a real type of animal. It can't just be an animal. But we still want this type because we want to be able to inherit from it, for one thing, right? We want everything to have a make noise function because we want the power of inheritance. And we also want to be able to create variables of that type because I want to maybe keep track of who my favorite animal is. Maybe A is my favorite animal, and my favorite animal could be a cat or a dog or a duck, right? That could change on the day of the week, or it could differ from person to person, but we know that they're all animals, so we need a variable which stores animals. We need the inheritance. However, we don't want somebody to just say, what's your favorite animal? An animal? That's not a normal answer. That person is weird. So they need to give you something specific. And that's where we have the abstract classes for. So we still want the type to exist. It's still useful to us, but we can't create things of that type. We can't instantiate them. And that was our idea of virtual and abstract, is the ability to redefine that behavior and whether it even makes sense to have a definition in the first place. Note that when you have something that is abstract, at some point you're going to have to give it a definition. If we just permanently say, I don't know how any animal makes noise, then that's not very useful information. If you pretend you don't know what noise a cat makes, then, you know, we still can't figure it out, and it's still abstract. So when you declare these abstract functions, you need to, at some point in some derived class, it doesn't have to be immediately, but at some point you need to define the way that function works. Here, when I say that the way a cat makes noise is it's meowing, that is the definition. So at some point I need to tell it how to do that, otherwise it still won't know and it won't make sense. Because of that, that's the other justification for why abstract classes cannot be instantiated. If you have an abstract function, it's not safe to call it because you don't know what it does. It does undefined behavior. It's not defined. So it's not really, it wouldn't make sense to call it because we don't know what it does. And a key distinction there, just to be thorough with it, is that it's not that it does nothing. Be careful there. If it did nothing, it would be defined, but it would just have no code. It's that it has no definition. We don't really understand what it means for it to do something. Right there, so there's a key difference there. Okay, so that was our virtuals and abstracts. Related to this, we did start talking about polymorphism. Which was the idea that data or functions can take on many forms. So poly being Greek for many, and morph or morpho being forms. And the answer is right there, right? It's many forms. That's the definition of it. It's very generic. You can apply it to pretty much everything if it has the ability to take on many forms. And we could say there's like dynamic. I'm going to use all the terminology just to have it out there. Dynamic, late, or runtime polymorphism, which was the idea that we cannot know the polymorphism until we run the program, until we can't really figure it out just by looking at it. And the other one, which was static, early, or compile time, where we can figure out exactly how the polymorphism works just by looking at it. Some structures we work with can technically fall under both of these categories, but just generically, templates in C++ always follow are filed under static or compile time polymorphism. These happen at compile time. There's no reason for them to happen at runtime, but something that could possibly be runtime polymorphic. Again, there's maybe context where you can figure out that it could do it at compile time, but I'm going to wave my hands and say at runtime or dynamically, we could do virtuals. And the example of that was the example that I gave here. So if I say animal A and the type of object that A is dependent on something we can't know until somebody sits down and types in a variable into the cin and it gets transferred to X. I have to wait for somebody to type 4 and then hit enter on their keyboard, right? I can't just tell whether this is going to be a cat or a dog by looking at it. I can't will that to existence. Because of that, the version of make noise that gets called, whether it's the cat version of the code or the dog version of the code, is dependent on something we cannot know until the program is run. That means that this is an example where it would need to be late binded or would be runtime polymorphic because it needs to run it to figure out how that polymorphism works. We can't know how this data changes until we get more information by running the program and getting what X is. Right? So virtuals were a possible example of runtime polymorphism or dynamic binding or late binding, whatever term you want to use, whatever you've read or gotten in lecture. Whereas templates, you can figure that out just by looking at it. And we'll use this as an opportunity to quickly talk about templates. Our intuition for templates was maybe we're writing a program where we have an array of names and we want to sort them alphabetically. And then we have an array of, let's just say, exam scores. And then we have an array of students. And maybe we want to find out who got the top score, and then also this program allows you to sort people alphabetically along with their scores, and then the students part has other information about them, like maybe their ID or something like that, right? So the idea here is that something like sorting is very, very useful for all three of these things. It's useful for names. You might want to sort strings. You might want to sort integers. You might want to sort even a custom class like a person. But if I wanted to do this, I would need to write my sorting algorithm, something like bubble sort, let's say. And if I write it to work with an array of strings, I'm going to have to copy and paste that code and write it a whole second time for the integer arrays, and I'm going to have to write it a whole third time for persons. And the sorting code is very useful. I might even want to reuse it in my other projects with other custom data types, or other data types in general, maybe bools or floats or whatever. But the idea is that we want to keep using the same code, but we would need to rewrite the code several times over, which is very annoying. When you have cases like this, where you're going to rewrite the same code, class declaration or function, but you want the type to change, you can use a template, and the compiler will do that for you without your need to copy and paste. So this is nice for two reasons. Firstly, it avoids the need to copy and paste things, which is just tedious. But also, it allows flexibility for anybody who might use your code. While I need my sorting algorithm to work specifically on an array of string, integers, and persons for this hypothetical program I'm writing where it sorts people based off of their exam scores, sorting is so useful that I probably want to use this in other programs, and if I'm writing a library or an API that I'm going to provide to another person or just put out for anybody to use, I want the flexibility that it will work with their code as well. So they might decide, yeah, I want to sort things other than integers and strings and persons. I want to sort my own custom class. I'm sorting matrices by the value of the determinant or something like that, right? I'm sure you could think of plenty of examples where you want to sort things that aren't these three types: strings, integers, and persons. So it allows that flexibility as well as avoids the tedium. So what you can do is you can put the word template followed by a list of generic types, which can be either type name or class. I've just chosen to do class, and then the name you want to give that generic type. So it's almost like a variable declaration. Here I'm defining this generic type T, and what this means is that anywhere I use T in my code, when I use this function later, this templated function, T will get filled in with that type. So what this means is that if I go up here and write bubble sort, let's just abbreviate that BS, and then int, what this will do is it will take this int and replace it here. T will get replaced with int, which means that it will generate code where bubble sort takes an array of integers. And I think I forgot my braces there. But then if I was to write another one where I say BS and then put string, in angle brackets, it will go and generate the same code, but T gets filled in with string. So the idea is if you know you're rewriting the same code, but the type needs to get replaced, use a template. Same thing goes for classes as it does with functions. Just, make sure that you put the generic type, in this case T, wherever you want it to be replaced. Know that it literally just does copying and pasting. It's something that you could do as a programmer, but you're just asking the compiler to do it for convenience because it's annoying. Because of the way this works, it would be an example of our static binding, or I guess not, this one isn't a binding, but it is a compile time polymorphism. So I'm sorry, I should be careful with my phrasing here. This is compile time polymorphic. That's because the compiler can do this because we don't need to run the program to figure out how this works. Just by looking at this, I know what I want is to sort an array of integers because this is an array of integers and I put it right there. So please just take the T and fill it in with integers. That doesn't require us to ask the user for external input, contact a server, read from a file, do anything weird, right? You can always tell that just by looking at it because the code will always specify, yeah, please replace T with this type. And it is just a copying and pasting process. It's really that simple. Because that is something that is able to be figured out without running the program, it is a compiled time polymorphic structure. And that goes for any template, whether we use it on a function like this or on a class. This will always be the case. Okay, so I think that about does it for our templates and our polymorphism. So maybe I have a few more topics to cover, but I want to circle back really quick before we get into later topics. I did skip over pointers just because I wanted to talk about things which were related, which were objects and polymorphism. Before we talked about pointers, obviously we needed to know about pointers in order to do things like virtuals in C++, which is why we talked about them first in the lecture. However, they're more unrelated in the grand scope of things, so that is why I saved it for here. So remember, what a pointer is in your computer, you have a thing called memory. And memory is just where everything is stored. Any variable you create in your program will get allocated into memory automatically. So this will pick some amount of blocks. In this case, an integer takes up 4 of these blocks called bytes, and it will say, yeah, these 4 bytes represent an integer, and whatever binary is there, 1101, etc., is what x is. It's the data which represents x. So you have many forms of memory in your computer, but generally RAM is where your variables and your program get stored. Your program itself gets put into memory. You'll talk about this in a future course. But everything that is currently running and being used by the program goes into your main memory is what we're talking about. RAM is usually what that is. So any variable you've created goes into memory, and a bunch of other things do too. Function calls go into memory, our program goes into memory. There's lots of things that go into memory. However, what this memory is in reality is just a line of all of these cells called bytes end to end. So the first one in memory is 0, 0, and then the next one is 0, 1, and then 0, 2, and then 0, 3, 4, 5, 6, until it runs out of cells to number. I'm keeping it small to keep things easy, but realistically this will be much, much bigger numbers than what I'm writing. And so we have the actual memory itself where the data gets put. So here the 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, whatever it is, the binary that represents the integer x gets stored in memory itself. And then we have a numbering system for every single cell that is in memory, and these are called addresses. So the address of x here is 0 because that's where I have put the data, where I've started putting all the 1s and 0s that make up the variable x. So if I set int x equal to 3, then this would be the binary representation of 3, which is 0, 0, dot, 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 0, 0, 1, 1. That will occupy all of this space, and the address of it is 0. A pointer is a variable which specifically holds addresses. We make pointers in C++ by simply putting a star after something. And we put a data type usually to represent what it's pointing at. Here, p is specifically pointing at an integer, and we do this to give extra context so that if it knows where something is located, it can figure out how to handle it. Integers are represented a certain way. Here there are 4 bytes, and they're represented as maybe 2's complement. But something like a character is only 1 byte. So if I have a character pointer and an integer pointer, all they store here is the address itself. P will hold the number 0, 0, which is where x is located. However, the address alone doesn't tell me what's there, it just tells me where it is. So the extra addition of the type integer in front of the pointer tells it how to handle that data. And different data types are stored in different ways, as you'll learn in future classes. And what this means is that it's kind of unsafe to use types that don't make sense. So if you use an integer pointer with a float pointer, that might not make sense. While they're both numbers, they're stored different ways. So the idea here is that a pointer is a variable type that holds addresses. And we generally represented this with some sort of arrow. So here P is pointing to address 0, 0 within our array, and it knows where that is. Or sorry, not array, within our memory. The ampersand operator was used to get an address of a variable. The address of X was automatically managed by the compiler. It picked a place to put it. If we want to know where it put it, we can put ampersand and it will tell us, and then we can store where it put it in a variable, which holds addresses, which is a pointer. Pointers are used to point to two different things in C++. Actually, that's not technically true, but in the context of our class, they pointed to two different things. I should be specific. And those two things that they can point to are arrays and objects. So now to circle back to our object-oriented programming, I can do something like this where I can call the constructor or a person object or I can ask it for an array of some many things. So this first one is an object. Notice that the thing that new is being used on is a constructor of one object. One person is being created with the new keyword, and P is pointing to that one person. In our other example, R is pointing to an array of 4 integers, and we can tell that because it's not using a constructor, it's using this syntax, which has the square braces, which represent an array. So the first one says, make one person, and here's where I put that person, here's its address, so you can look it up later. And then we have the array. We've made 4 integers consecutively in memory. They're all next to each other. Here's where we put them. That way you can use it later. So remember that you can, after you allocate a pointer, right, you can do whatever you would do normally with that array. It's just, this is the way you dynamically allocate it. So there were two things that we could point to which were dynamically allocated for our program, which were objects and arrays. You can technically also do lambdas / functions in C++. That's the other thing that I was kind of waving my hands around, but that's outside of the scope of this class. So for the sake of our argument, it will just be an object and an array. And because of the way that a pointer works, it is just an address. All this is getting is some really long number when we do new person and new integer. The context on whether it is an object or an array needs to be maintained by the programmer. If I just go and use P later and I know that P is a pointer, without somebody telling me that it was pointing at an object, I might not know whether it's an object or an array. There is no way to tell that without extra information being kept, either by the runtime environment or the programmer just leaves a note and says, hey, this is what this does. So when you're using these in practice, please, 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 as you always should with any code, leave comments, tell people what you're doing, don't just expect them to figure it out. Right, so that was how we use pointers in our actual code. Just as some quick reminders, arrays can be used exactly how they were used statically. Right, there's no difference here. This will go into this array of 4 things, and the one at position 1 will get set to 2. Oops. And when we're using objects, if you wanted to use the dot operator, it gets replaced with this arrow, which is, I'm writing it as an arrow, but when you type it, right, is a dash and then the greater than sign, which looks like an arrow. Actually, let's just keep that. And so I could say something like P name equals John, and this does the same thing as the dot operator, but C++ makes you specify whether you're using a pointer or whether you're using an object. If we're using an object, use a dot. If you're using a pointer, use an arrow. And then I'm going to wave my hands because we talked about it in class in detail, but remember that we went into examples of when you might use these, the advantages of using a pointer versus not using a pointer, which was the fact that it's simpler to like transfer data, right? If I want to help multiple students, it's more helpful for me to give everybody my email address than it is to go to a cloning machine and make a separate copy of myself. So the pointer is a reference. It's kind of like a lookup or a name or a contact information to figure out where the address of something is and go to it. So I can give everybody my email address and they can all figure out how to contact me. That's what a pointer is, rather than objects where they make completely separate copies every single time you use them. Related to that was the idea of a deep copy versus a shallow copy. So if I had a person P and I create them in my code to rename John, and then I have a second person Q, and I set them equal to P, what this means is that P points to some object and Q points to the same object, who has a reference, which is just an address. And there is this person, John. John's contact information, John's reference is hex 0A. This is some random number, it's an address, but I want you to think of it as contact information or as a name to look it up. What we're doing when we say Q equals P is we are saying that P and Q, which are variables which store things, are going to be set to that address. So what this does is when we say P equals new person John, we create this person John whose reference is hex 0A, and because pointers store references, P stores hex 0A. When I set Q equal to P, because they are both pointers, what this does is simply set Q equal to what P is, which is hex 0A. What this means is that if I do something like q.name, or sorry, arrow, right, because we're using pointers, q arrow name equals Jane, we maybe expect Q to be a second object. However, because we're using pointers, using references, what this will say is go to what Q is pointing at, which is hex 0A, this bubble right here, change its name to Jane, which will overwrite the John that was there. So what we've done is we've indirectly changed the name of P via Q because they're both talking about the same thing. They both have the same lookup information. They both are referencing the same object in space. When we do this, it is called a, sorry, not a deep copy, a shallow copy. And this is what I mean by that, you have an email address kind of thing, is both P and Q have the same reference to the same guy. They both have my email address. So if they're contacting me, if P writes an email to Samuel Black at unlv.edu and Q does the same thing and writes an email to me, I get both of their emails. Right? So they have the same contact information. When they go to look up or do anything with that contact information, they're going to end up at the same place. This is compared to a shallow copy. So say again, we create a person whose name is John. And then we create a second pointer to it. But we don't initialize anything about it, and now I set q.name equal to p.name. Sorry, arrows. I was just on about that. I forgot. Q arrow name and p arrow name. Then what this will do, the first line will create at an arbitrary address, a person whose name is John. And in the second line, we'll create a person with no information, but they obviously get an address. And Q and P will point to their respective objects. So because we have two different allocations, I have a new keyword here, and then I have a new keyword here. When I do the new keyword on this one, it will create this bubble in space with a name of John. P will refer to that object because P gets the allocation that was returned by new person. When we do person Q equals new person, it makes an entirely separate new person, an entirely new bubble, and that's who Q points at. So when I do Q arrow name equals P arrow name now, it will set the name of what Q is pointing at, this C3 bubble, to the name located in the 0A bubble. So this would be that cloning example where I said earlier, where you have two different people, but they have the same information. So now if I contact hex 0A and hex C3 in the context of my analogy, these would be different email addresses. So while they maybe go to different people, one would go to my clone and one would go to me, and we just have similar email addresses. Maybe they append a 1 to my clone. They start labeling it. Right? But the idea here is that they're completely separate and distinct from one another. So if I go and change things later and do something like Q name equals Jane, this will change the name of just Q now because it's its own independent bubble from P's bubble. So they each have their own separate objects versus before where they're both referring to the same person. They're both referring to the same object. And when we do this, this is referred to as a deep copy. So a deep copy just being when you have separate versions of the same data. So once I set the name to Jane, it's no longer a deep copy, I suppose. But when it was still just John, that is a deep copy of the same object. I've essentially cloned it and made an entirely separate person with the same information, but they're their own individual, rather than just given the contact information out, given a reference out for the same bubble, the same object. And you might want shallow copies and deep copies for different applications. If you don't want changes made to one variable to affect the other, then you definitely want a deep copy, right? However, a shallow copy is more memory efficient because when we do transferring, all we're transferring is the email address. If I was to change my office at the university and it went to a different room, as long as you have my web page or my email address, you can just ask me and you don't have a clone, right? It's easy enough. So if you want to look something up, you can with a shallow copy. You just hand out, references to people. So shallow copies are quicker. We don't have to have duplicates. So in this one we have two bubbles, whereas this one we have one, right? So there's less memory is taken up in this first one than this is the second one. So if you don't care, make a shallow copy because it will be faster. But if you need there to be distinct data for each object, then you want a deep copy because they need to be separate to solve your problem. Okay, so I think that about does it for an overview on pointers, at least. I think where we left off on non-pointer topics was templates, and what came after templates in our lecture should have been operator overloading and exceptions. So operator overloading, say we're given matrices from math like this. In mathematics, if you wanted to do something with these matrices, you might write A plus B. However, if we're implementing this in a programming language, I would have to write a class called matrix, And then it would need to have a 2D array for the numbers. And then probably an integer for the width and the height. And I would write all this stuff, right? I would implement the class, I would decide what variables it needs and what functions would make sense. However, what this means is that if I wanted to write something like a plus b, I can't do that because I'm doing it with a class. If I just write a plus b in the code, it has no idea what it means to add two matrices because I have to write the code that does it. So I could very well write a function called void add, or I guess matrix add, which takes two matrices and then does the code to add them together, right? Allocates an array, adds them element-wise, does whatever matrix addition does in mathematics. However, if I write it in the function notation, it doesn't necessarily translate directly to this in terms of the way I read it. So they're functionally equivalent. They do the same thing if I just write out the code, right? It doesn't matter. But it doesn't look as nice, and that's the main reason why we use operator overloading. Now, operator overloading exists strictly in C++. You can maybe argue it does some other things, but the main idea behind it is it just makes your code more readable. If you're using things which have some mathematical terminology associated with them, or notation, sorry, not terminology, but notation associated with them in the real world, you maybe want to translate that notation over to it in the programming world just so that it's easy to read and looks nice and people will get an immediate understanding of what it means just by looking at it. And that's when we do this operator overloading. Operator overloading just means that we take an operator. In this case, our operator here is plus. It's the thing which is the operator. The other two things are the operands. And we basically just write a function, but tie it to that symbol. The symbol here being the plus sign, we make a function whose name is that. So when we write these, the way you write it is exactly as you would write a normal function, which is the return type, then the name, then the parameters. I'm going to write this a specific way first. So if I wanted to write my function, right, it would look something like this, where I would say, here's a function which adds two matrices. It returns a third matrix as the result of adding A and B. Here's how we do it, squiggly. There's the code. Right, so it's return type, name, then parameters. An operator overload is just a special kind of function where the name is instead a symbol. So here, if I wanted to overload the plus operator, I would replace the name with operator to say that I want to do an operator overload, and I wanted to overload the plus. And now what this will allow me to do is anytime I write a plus b in my code, it will know that I'm talking about an operator and call this function that corresponds to that operator. So it's really just like an alias. You're writing a function, but it's a function with a special name that just makes it easier to read. And that's really all an operator was at a high level. However, we had some specific implementation details about how operator overloads work in C++ because they do have some caveats and they're maybe not completely intuitive. So I think this is the intuitive way to write operator plus, is to say, well, it returns a matrix and it takes two matrices as input because that's what plus does, right? If you were writing it in mathematics, you would write C equals A plus B. Here's the matrix which stores the result, and then we add two matrices, and plus always works on two things. So it makes sense, I think. However, in C++, you have the ability to do operator overloads as either static or non-static. The ones which must be static are the two stream operators. The ones which must be non-static are equal and all variations of it, so plus equals, minus equals, divide equals, etc. And the indexing operator overload. And then everything else can be either static or non-static. It is your choice. Although it is recommended and I guess convention to do everything non-static unless it has to be static. So there are some special cases where other operators might be done statically as well. You could do plus as static. Basically, things need to be static if the first parameter is not the class you were writing the operator for. If the first thing was like an integer or a float, or in this case, when we work with these two, it's always a stream, like an iStream or an OStream, then you should probably write it as static. And then these ones should just always be non-static. There are a few that we cannot overload as well. And I believe I know all these offhand, but I'm hoping I'm correct. So the first one is the ternary operator, which is question mark and then some stuff, and then a colon and then some stuff. The dot operator, you cannot overload. However, the arrow operator, you can, which is a little bit strange, but it is allowed. And an operator which we didn't really use in class, which is the size of operator, which tells you how many bytes a thing is, can't be overloaded. And then I think the last one is the scope resolution operator, which, if you remember, is just used to access static variables and used to define functions, which, while they may not have the static keyword, are static from the compiler's point of view in terms of how it implements them. So it kind of needs that to be consistent. That being said, you don't typically use these on objects anyways. So I think that's pretty straightforward. We don't want to overload any of these guys. Really quick, let's just talk about how we do static and non-static implementations for these. So let's say we have our matrix class, and then we will write a static and non-static implementation. We would write our declarations within the class itself. We'll just make these public and assume that I wrote whatever variables are necessary up here. So let's say we write the plus to be static, because that's what I did earlier. What I might do is do friend matrix operator plus matrix A and matrix B. And this is our static implementation. And then our non-static implementation would look something like this. Matrix operator, let's just say we choose to do multiplication as non-static matrix B. Static, I think, is fairly intuitive. This is how we expect plus to work. It's a function which takes two matrices, adds them together, and returns a third matrix. Pretty straightforward, I would think, right? If we had C equals A plus B, A gets plugged in for A, B gets plugged in for B, and C is the result, right? However, that's not the way things work when we do things non-statically. So if I wrote C equals A times B, this still does return a matrix, and B gets plugged in as the parameter. However, A becomes the caller of the function. Remember from when we discussed what static and non-static meant earlier, is that non-static means that there is an object who is doing the action, because non-static inherently means that the thing is tied to an object. In this case, what we do with operator overloading is the first one that appears in a non-static operator overload will always be the caller, and thus this when you write the actual function itself. So A here will become this, and the framing is a little bit strange, whereas the static implementation we would say A and B are being added together, which is just like a like a common sense way to think about mathematics. This one, what we're saying is A is doing the multiplication and B is the one involved with it. So we're inherently saying one of the objects is responsible for doing the action by saying something is non-static, and that's what this means here. So while both can technically be fine, and it doesn't really change our implementation much outside of the need for this, I think the framing of the first one makes more sense inherently. The second one's just strange, although it is how you should implement things in C++, so obviously we should mention it in case you encounter it. Right, so that's how we did our implementations. Our other difference here was that because this thing is static, in C++, for whatever reason, you cannot mark operator overloads as static class members. It does not allow you to do that. It's very strange. This is a C++ thing. Other languages will allow you to do that. But here, if you want an operator to be static, you simply write it at global scope. Global variables are static, and then you have the option to mark it as a friend. So remember that what a friend is it can access all members. That means it ignores the private and protected modifier and just accesses whatever it wants, so it breaks the point of a private and protected. But this doesn't mean that operator plus is a class member. I would write this globally. I would write out the whole function in global scope. Friend is just simply saying, my friend is out there somewhere, here's their name, so when you find them, we know they are the friend, and they can do what a friend does, which is ignore private and protected. The non-static one is just a class member. It belongs to the class. If you implement it, it has the matrix : : in front of the name. It is just a class member. It works how you'd expect it to. So friend is a caveat here. It breaks object-oriented programming paradigms, and it's just the way that it's chosen to be in C++ rather than make it static, which I think would make sense. But that's how C++ is, and so you're aware that's what it does. All right, so remember we did this in class. We did a few examples, so I won't write it completely out. The other thing is, remember when you have a non-static implementation, because the first object is this, you'll always have one fewer parameter than you would expect. So plus is a binary operator. You expect it to take two things. When you write it statically, it does have two things. You have matrix A and matrix B. However, when you implement it non-statically, because the first one is implied to be this, when I write A times B, A is this, it's the caller. That one does not need to be passed as a parameter anymore because it's the one doing the action. If you want to access it, you could use the this keyword. And because of that, it will only take one parameter, even though multiplication is a binary operator and you expect it to take two things. So an important thing to remember as you implement things non-statically, because that is the convention in C++, and it's not necessarily intuitive. Okay, so that was our operator overloading. There's a way to increase readability, and the implementation details are kind of the tricky part in C++, but generally, if you're looking to do just general programming, remember that it is just a function whose name is a symbol. So you can replace the name with operator and then the name of the operator, and it will work. Other languages don't have this restriction, but since we're doing C++, it's important to go over. The next topic we talked about in class were exceptions. So consider if I'm writing my operator overload with these predefined matrices that we had, there are some combinations of these which are invalid. A plus B is valid to do because A and B are the same size, and the way matrix addition works is that you add things element-wise, so the 1 goes with the 5, the 2 goes with the 6, the 3 with the 7, right? But I couldn't do this with A and C because there's these extra numbers out here which don't line up with the 1, 2, 3, and 4. So if I did something like A plus C, then this is undefined. We have no idea what this equals because it shouldn't even be done. It's an invalid operation. So when you have something like that, we might check in our code if, sorry, this I guess would be in our operator overload for plus, right? So we'd have a matrix returning function called plus, and it takes two matrices A and B. Then we'd have our code down here, which actually adds the two matrices, but we have this potential error where we shouldn't add A and B, and that happens if the A dot rows does not equal the B dot rows, or the A dot columns does not equal the B dot columns. Basically, if either of the dimensions don't match, then we can't add them because they're not the same size. Right? And if this happened, what we would probably think is our first idea is, well, we should let somebody know that this was bad. So maybe tell them, print an error message. But if we leave it at just this, if we just print an error message, then this still isn't really complete. Because what I've done is I've simply checked if something bad happened, I've let the user know, but I've done nothing to stop it. This code down here, which is the matrix addition code, or whatever that is, that adds these two things, is still going to happen. We're just going to keep going after this if statement, and we're going to execute code, which probably shouldn't be executed because this is not a valid operation to do. And there's two reasons for that. One, it's an undefined mathematical operation, so it doesn't have an answer. We shouldn't waste time executing code that's not going to give us anything meaningful. But B, from a non-mathematical point of view, we know that matrices, for example, are going to be implemented with two-dimensional arrays, and so there might be a seg fault if they go out of bounds because one will try to access data that simply doesn't exist. So there's a possible crash here. We don't want this code to execute for a couple of reasons. Okay, well, that's fine. We can just return from the function. But this on the face is not enough. And the reason being is we're returning. This will bail from the function, so it won't go down to this additional code. However, this function is supposed to return a matrix. But I'm just returning. I'm not returning anything in particular. So I could return a matrix, but now I've still kind of broken a rule here. I'm returning some matrix which is a matrix but maybe doesn't represent anything in particular. However, that's really not great because when we think about the mathematical operation, it's undefined. It shouldn't return a result even if it is just an arbitrary placeholder. So from a design point of view, we either need to return something which represents undefined, which is a little tricky here unless this returns like a pointer. I think this is probably not ideal. Or we need it to not return anything at all. And in this case, I'm going to go with that second definition. When you've encountered a scenario like this, where you have no idea how to proceed with the code, and a return does not seem appropriate, and you still need to signal to whoever is using your function that an error has occurred, then you might throw an exception, or throw something in general. The syntax for this is throw and then some object. So notice here what we're doing is we're calling the exception constructor. The exception is a class that exists. I'm simply saying here's the constructor. It has both a default constructor and a constructor which takes a string or a character pointer, which is a message just about what the exception was. Here I'm going to be lazy and just put error, but you could put something more detailed that says there was a dimension mismatch. I can't add these, right? And so what a throw will do is it will pause the execution of the program. And it will look in all scopes it was enclosed in one by one for a way to catch it. Remember we talked about try and catches, which are ways to handle a throw. Here I have no try and catch, so what this will do is it will bail completely out of the plus operator because it sees no way to handle this exception and go to whoever called it. So what this will do is it will check every enclosing scope, whether that be ifs, tries, fors, whiles, or function calls, and just work its way up until it finds an appropriate way to catch the exception. If my usage of the code was something like this, where I said try to do A plus C, and then catch an exception, what this will do is A plus C generates an exception. It will pause the execution of the program, so it will stop doing A plus C, and it will take a moment and say, well, I can't really proceed any further. I need to find a way to catch this. The try block that this is contained in is this one right here. There could be more try blocks outside of this, but because this is the closest one that it is contained within, it will try this try block first. So we'll try this. It will say, well, I didn't know what to do, and then it will catch the exception and execute this code. So in this, you might have something like C out, E dot what, and then you might write extra code to handle the exception, to do whatever, addresses the error that occurred. You might have a third matrix D, which relies on A and C, and now that you don't know what D is, it's an undefined value, you might have to find a workaround, right? And that code will go in here. So you would catch it and then do something in response to the catch, handle the error in some way. Remember that catches are done in order. Here I only have one. However, if I had multiple, then I would check them in order. So if I had a catch for both a logic error and an exception, then it will check the logic error first, and then it will check the exception afterwards. And in this case, because it throws an exception, it will go to the exception code down here. And then finally, you might have a catch, ... is used to catch anything if you don't care about the type. We also talked about in class that the order that you put these in matters. The logic error and exception, specifically in this example, have an is a relationship because the logic error inherits from the exception class. Inheritance will still work, and because it does it in order, if I throw a logic error, it will catch it with this logic error catch. But if I flip the order of these, if I had the exception first and then the logic error afterwards, and I threw a logic error, it would catch it as an exception before it ever got to the logic error case. So remember, we talked about you have to put these from the most specific class to the least specific class, otherwise you'll have catches which are unreachable. Then the other last thing was remember that you can throw anything. So while I've put exceptions here, you can put ... and it will catch anything. You can throw integers, you can throw floats. You probably shouldn't, but it's C++, it's the Wild West of programming. Do whatever you feel like, I suppose. But that's kind of the point of the exception class, so I would say avoid it. So remember, kind of the point of our exception class and inheriting from it is that we allow people to catch things just generically. And this is nice because if you hand out your code to somebody, you've written an API or library, you can make your own custom exception class. And if you have multiple of those for special different circumstances, like I have an exception for multiplication errors and an exception for addition errors and an exception for subtraction errors, right? I can give the programmer flexibility to catch all of those separately if they want to handle addition and multiplication and subtraction differently. If they have a bunch of lines of code in their try block that all could potentially generate those exceptions, then they have the flexibility to handle those exceptions in a different way. However, if they don't care, they don't want to read through your documentation because it's long, or they're using multiple APIs, they're using your code and the code of somebody else together to make a full program, then they don't have to care. They can just catch an exception, and regardless of what kind of exception it is, regardless of what the derived class is, it will still catch it because it has an is-a relationship. So you're offering flexibility to a programmer to either just generically catch an exception if they don't want to have that granularity and distinguish between all the different types of exceptions, but you also are allowing them that granularity if they do care about it. And then generally, if you yourself are writing tries and catches, you want to do this over code that you think might be unsafe, either if you just don't understand completely how it works because you haven't read through the documentation or there is no documentation, then just put it in try block. It probably won't crash. So it's intended for unsafe code. Which is either just you maybe don't fully understand how that code works, or it's not documented, or alternatively, just you don't know what the input could be and you maybe don't understand all the edge cases. You could be getting data from a server and you have some expectation that it's going to work this way, but a programmer 3 years from now might modify your code and modify the server, and they might do things which cause your code to break. So just to be safe, put in an exception, put in a try-catch block for exceptions, so that if they break something, the whole application doesn't crash. Or if somebody hacks your server and modifies your data and makes it ill-formatted for your program, then your program doesn't crash, right? So generally, if you think something could be unsafe, put it in a try block. It will not crash your program as long as you have catches. Right, so that was our high-level view of exceptions. The next topic from class was recursion. Recursion is when we define a problem in terms of itself. The example that we did in class was with factorial. If I had a set of numbers, n, and I wanted to do n factorial, and the result up to, let's just say 3. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1, 1 factorial is 1, and 0 factorial can't be written this way, right? But is defined as 1. And the idea here was that this 2 factorial is the same as this 2 times 1 up here. This 1 is the same as this guy right here. So we notice that there's a pattern where every factorial can be written in terms of another factorial. And specifically what we came up with was that if I want to take the factorial of a number n, then it's equal to n times n minus 1 factorial. And what this means is that we can take a operation or a function and define it in terms of itself. Factorial here is now defined in terms of factorial. So we have some level of recursion. And then we have some non-recursive part, right? So this is non-recursive. In our actual problem itself, we have some defined cases. 0 factorial is equal to 1 because that's the way it is. Notice that 0 exists outside of the pattern. we can't write 0 as all the numbers below it until we hit 1, because there are no numbers between 0 and 1 counting downwards. 1 factorial also can't be written in terms of that because it's the last one. If we do 1 and all the numbers underneath it, well, there's none left just because it's the stopping point, right? So we have are these two things, which we called base cases, which serve as stopping points for our recursion. And these can occur either when it's trivial to solve because the problem can't be defined in terms of itself anymore. Here, I can do something like 3 factorial is equal to 3 times 2 factorial, but I can't really do that with 1 factorial because 1 factorial is not equal to 1 times 0 factorial. Well, it is, I suppose, but 0 factorial, for example, is not equal to 0 times negative 1 factorial, right? So I guess that's a better example. So no, this doesn't work, right? It's trivial to solve. We cannot write it in terms of the same problem, so perhaps it's not the best definition. So we can have base cases in any case where it's trivial to solve. Either there is no further work to be done, or it's just by mathematical definition, 0 factorial is just 1, so it should be 1 when we define it. Right, so that was our base cases. And then finally, what we needed for recursion was a reduction operation, which is some sort of operation. Reduction here just means it changes the problem. It doesn't necessarily have to mean smaller. Remember that reduction in computer science does not always need to make the problem smaller. Even if it does in this example, it just means to change it. And this works because if I had something like 3 factorial here, and that relies on 2 factorial, then I can do 2 factorial equals 2 times 1 factorial, and then 1 factorial equals 1. So notice that what the reduction operator here does is the number that we're taking a factorial on decreases over time until it hits one of our base cases. So the point of our reduction operation is to reduce or change the problem in some way so that the next recursive call will approach the base case in some way. That can be either actual like mathematical operations like subtraction where we're subtracting a number, or just anything that transforms the problem. If you remember from our homeworks, we did things where, for example, we followed pointers and those reduced the problem as well. As long as you modify some state of the problem, you modify variables in some way, then it will approach a base case in some fashion. And so we'll leave it kind of high level like that. We did a bunch of examples in class. In the context of programming, all recursion meant was that it's when a function calls itself. If I wanted to implement this factorial function, I would do something like this, where I would say int n, and then we would first do our base cases, or say if n is equal to 0, then return 1. And then else we do return n times factorial of n minus 1. So remember, our base cases kind of served as a way to act as a stopping point. If I didn't have it, it would keep calling forever. It would keep doing n minus 1 indefinitely. But really, in the context of our programming, it is just when a function calls itself. I think that about does it for this high-level view of recursion. I am realizing that this video is getting rather long, so I will put in the description a part 2 where we talk about all the material which is relevant to specifically the final exam. We'll maybe talk about recursion in more detail, but that video will focus on linked lists and stacks and queues. So I would say look out for the description. I'll try to get that out soon, and I will see you then.